Okay, welcome back. So after having evolving particles on static networks, now we will have a talk about evolving networks by Shankar from UNC Chapel Hill.
Thank you. Yeah, so and also, having attended lots of really good talks, at some point there has to be a regression to the mean sort of average. So my goal here, I'm going to take a hit for the team. So this will be back to sort of a bad talk. So I'm just going to sort of tell you a brief, so I'll start with a brief motivation and structure. And maybe the first 5 minutes of the talk are important. After that, you can completely zone out. But the plan is the main parts of the talk, there are 3 different settings where somehow what one might expect in dynamically evolving networks, and this is something that Lutz also gave a beautiful talk. So what you might think happens doesn't quite happen. So the first topic is sort of seed detection in dynamic networks. The second is sort of change point detection. And the third is sort of co-evolving networks at a very baby level. So I should mention, so all of this is a joint work with Sayan Banerjee, and then parts of this are work with Ian Carmichael and Zoe Huang. Okay, so again, so first part, right now I'm going to quickly tell you the motivations of the 3 problem areas. This is the only important bit. Rest are specific contributions you might not care about. Sort of the main thing the case I would like to make is there are lots of interesting problems, and even like baby questions in this area are completely open. Okay, so the first question is sort of seed detection in evolving networks, trying to understand when, let's say you have an infection spreading on a graph or something, and you don't quite know where the infection started from. Maybe you know who has been infected, and you want to understand who is patient 0. Sort of more precisely, suppose you have some sort of dynamic network started from a single node or some seed graph, and you observe the network when it is of a super large size, let's say 1 million nodes. And now, so you know who is infected, maybe even connections between people on the network, so who might transmission paths, but there's no temporal information. You do not know who is patient 1, patient 2, and so on. You only know the network topology. And now you're given a fixed budget, a budget of size 30. So main point here is sort of independent of the size of the network. And your goal is to output 30 vertices in the graph such that with high probability, your seed is in the output set. So can you do this? Again, the main math, non-trivial math fact not found by me is in many cases, you can do this for families of graphs. You can come up with a budget independent of the size of the network where you can find patient 0. The second area is sort of change point detection. Change point in time series is a very classical question in statistics. So for example, life expectancy, if you have sort of time series, when are there sudden changes, abrupt change, something shocks the system, and then there's an abrupt change in the time series. So for example, life expectancy, there are various sudden shocks to the system in the US where there's sort of a drastic drop all the way in during. So it's still to be seen how much the pandemic will cause a drop in the life expectancy in the US. But so the basic question is, in the context of networks, suppose you have some sort of temporal network data, and it could be the adjacency matrix of a graph. It could be time series observations at each node of the graph. And now suppose at some point in time, the network experiences a shock. Then the question is, based on, let's say, observations of the network, can you detect this change point? And in particular, to make math statements about this, you need to know how does this shock change structural properties of the network. So this is the sort of second area that I'd like to tell you about. And sort of the third area is sort of network coevolution. I didn't realize, there are all these superstars here, Frank, Siva, Adrian, thinking about these problems. Kavita mentioned these. But ours is a much simpler question, but the motivation is similar. So most real world network models, they support some particular purpose. So for example, diffusion of information, that's the purpose of, say, Twitter. But in many cases, sort of the network influences individuals. So if I'm on Twitter, I would get information from Twitter, but then I would also influence the network. Maybe I follow other individuals in the network. And so now this opens up other chains of information propagating on the network. And to a large extent, lots of, at least theoretical work is, they keep these 2 things separate. There's either dynamics on a fixed network, you have random walks or epidemics on a fixed network, or the network itself changes, but there isn't necessarily a dynamics that's influencing this. And so my main goal here is for a very super simple math model, I would like to, there were some conjectured phase transitions, and I would like to tell you about these phase transitions. And so what is the universal story behind all the models I'll tell you in today's talk? So all the network models will have the following structure, where you have some sort of network at time 0. At each stage, an individual enters the network and tries to form connections to pre-existing vertices using some probabilistic dynamics. So that is the unifying theme in all 3 stories. Okay, so sort of that's it. So now you can sort of completely zone out here. So first question, seed detection in evolving networks. So again, this is the basic question. Come up with an algorithm which doesn't depend on the size of the network, which allows you to track down the source of the infection. So the simplest model of such an evolving network is the so-called preferential attachment model, where you start with some attachment function f. And so now you start with a single vertex, and at each stage, a new vertex enters the system and connects to one pre-existing vertex using something. And let's say, to keep things simple, we say that a person with large degree, they're more likely to get connected, and how popular you are, that depends on this function of your degree. Okay, so this function could be sort of constant, and that means your degree has no role to play. People just come into the system and randomly connect. Or you come into the system, if it's an increasing function of degree, the more individual friends you have currently, the more people want to connect to you. So that's sort of preferential attachment type behavior. And we're going to call tau n to be the network of size n. Okay, so I wanted to use the iPad here, but so a random recursive tree, that basically means at each stage, a new vertex comes into the system. It doesn't care. It just connects to someone randomly in the network. Okay, so the degrees don't play any role. Sort of, you can simulate this, I think, around 3,000 vertices. And so somewhere way in the middle of the tree, suppose I just plot the network without any temporal information. The network started over here. So the red vertices, I think this is vertex 1, this is vertex 2, and this is vertex 3, sort of shows up slightly weirdly, but this is where the network started. Okay, and so again, what is the question? If I just gave you this tree, can you identify, and I told you, I'm going to give you a fixed budget. You are allowed to output 20 vertices. Can you tell me where the tree started with reasonable probability? Sort of a much simpler model for these sorts of questions is sort of preferential attachment, where if this is the structure of the tree at any time, then the popularity of this vertex is 2. This vertex has popularity 1. This has popularity 2. This vertex has popularity 3, 1, and 1. And so then you connect with probability proportional to the degree. So people with more friends get connected with higher probability. And so here, if you just look at vertices, so again, the network started over here. So it looks kind of red here. And intuitively, if you know if you know degree information, sort of trying to go near the vertex with the maximal degree will give you a good idea of where this network actually started from. Okay, so sort of this area started with like fundamental work of a whole bunch of people: Bubek, Dubroy, Lubushi, Elkanan, Miklos, Jogan, Low, and so on. And there's sort of a math definition of what a root finding algorithm is. And essentially what it's saying is, suppose you have some temporally evolving network. And now at some stage n equals 1,000,000 nodes, you remove the labels. So labels represent when vertices enter the system. You remove the labels, you just give, you're just allowed access to sort of the topology of the network, no temporal information. Then the question is there an algorithm? So namely a mapping that takes your network and outputs a subset of the network. And what you'd like is the following. So someone has given you an error tolerance epsilon. Then what you need to do is you need to come up with an algorithm which has some budget k. This k would depend on epsilon, such that the algorithm that you've come up with. So again, the algorithm takes your network, outputs a subset of the network. It only uses topological information. It only outputs k vertices. But what you would like to happen is for your probability model, the probability that your vertex 1 belongs to the output set, the probability of that is greater than or equal to 1 minus epsilon. Okay, so k should be independent of the size of the network. It doesn't matter whether you have 1,000,000 nodes, 1,000,000,000 nodes, trillion nodes, etc. You should just be able to do this. So that's the basic question. And in particular, how does this depend on epsilon? Okay, so would, for example, yeah.
Expectation that the microphone goes to zero. Microphone. The dependence in epsilon means you mean that as n gets larger, you want epsilon to go to 1 in that sense.
No. Okay.
What do you mean by that?
So good. So epsilon is given to you, and what you would like is if epsilon is smaller, naturally you need to output a bigger set, right? And so the question is an order 1 over epsilon enough? Is your budget 1 over epsilon? Is that enough? Is 1 over epsilon squared, or do you need like 1 over? So first off, it's not even clear that you can do this without, say, outputting log n vertices or something. Something that depends on n. Sort of the remarkable finding of these people is for a whole class of models, you can do this. But now the next question is, how does this depend on epsilon on for your probability model? Okay, so sort of that's the first question. And the most natural classes of these C detection algorithms is, so you don't have temporal information. So you look at your network, you compute some sort of centrality measure of every vertex in your network. So for example, you can look at the degree, or you could look at something called Jordan centrality, which I'll come to. But your favorite notion of centrality, and then if someone tells you you have a budget of K, then you output the top. Top would be the smallest or largest, depending on how your centrality works, the top K vertices. Okay, and so once again, so you say that these sorts of algorithms have error tolerance epsilon for a given choice of K, if the probability that your seed belongs to what you want in your outputted set, this is greater than or equal to 1 minus epsilon. Okay, and so answering sort of Siva's question. So the main question in many of these probability models is, how does this depend on epsilon? Is it 1 over epsilon? Is it 1 over epsilon to the 100? 1 over epsilon to the 1000, etc. How does it depend on your error tolerance? How much budget do you need? And there's sort of a related question, which someone said is related to topological data analysis, which I have no idea about, which is a notion of persistence. And so here the question is the following. So once again, if you have a sequence of, let's say, growing networks, so the networks are all sort of coupled, then you can ask, so is the degree, maximal degree, is that persistent? So namely, is there some finite time, finite random time, let's say within time 1000, after which the identity of the maximal degree does not change? So after time 1000, whoever has the maximal degree, they will forever have the maximal degree. Okay, with probability that of course depends on this 1000. But if something like this happens for a centrality measure, then potentially that suggests that you can use that centrality measure to define seed finding algorithms. Because basically what this is saying is, within some finite time, the, let's say, degree fixes itself, the identity of the maximal degree fixes itself. So you go to the maximal degree and your root will be somewhere near that maximal degree. Okay, so all of these are sort of hallmarks of long-range dependence, sort of the origin. If you have an evolving network model, somehow what happens way back in time has a major impact on how the network itself evolves. And this is what also Lutz sort of alluded to in his talk. So the finding of Bubek, De Vrooy, and Lugosi is the following. So for a bunch of network models, the following centrality measure actually works. So max degree centrality doesn't work. It's sort of easy to check for, say, the random recursive tree where things are randomly connecting. So what they found is the following. Just a note, this centrality measure is only defined for trees. So it's a big open problem. If you have network information, how do you do these sorts of questions? But suppose you have trees, then what you can do is, okay, you're trying to check did the network start from this vertex? So one thing that you could do is, okay, this vertex has 3 children. If it did start from here, it has 3 children. So you look at the subtrees hanging off each of these 3 children. There's one over here. So the size of this subtree is 1, the size of this subtree is 3, and the size of this purple subtree is 9. And so the centrality of a particular vertex is the size of the largest subtree of a child of V. Okay, and so the basic idea is, suppose I say, did the network start here? So I look at this vertex, it's a leaf. The size of the centrality score of this vertex is the rest of the graph, which is n minus 1. So you don't maybe expect that the network started here. And so the larger the score is, the less likely you are convinced that maybe the network started from there. So somehow the more within the middle of the network you are, the smaller this score will be. And so this was sort of first analyzed by Bobek, Devroy, and Lugosi. And so what they did was they sort of thought about this for two classes of models, the preferential attachment model and the random recursive tree. And it turns out there, because of connections to Polya-Ern schemes, you can do lots of exact calculations. And in a beautiful paper, they found, how many for a given epsilon, what should be the budget of your algorithm, so that if you use this centroid centrality score, you're able to find the root with high probability. How does that depend on epsilon? And so sort of what we carefully thought about was, suppose you have some general attachment model. So the way that your network evolves depends on some function. If you have sort of if you know something about this function, then if we derived sufficient and necessary budget requirements using the centroid centrality score. So if you're going to use that particular centrality, then it turns out that if you have so much amount of budget given an epsilon, if you have so much amount of budget, forget this, this much amount of budget, then with high probability, so probability greater than or equal to 1 minus epsilon, irrespective of how large the network is, the output that you give will capture the origin with high probability. And again, if you're going to use that same centroid centrality score, you need sort of at least, I think the error should go the other way. Oh, okay, sorry. So this is sufficiency bounds. So depending upon the properties or assumptions that you make on your function, you can derive sufficiency bounds. You need at least so much. If you have so much, then it's enough. And sort of also necessary bounds. So you need at least sort of same order of magnitude.
So I assume your F is always monotone. It can't make it more likely to connect to less degree vertices.
Very good question. No, it does not have to be monotone. There are technical conditions on the F, but it does not have to be monotone. This is basically saying, it's bounded in a linear fashion. And there are some more technical conditions, but it does not have to be monotone.
Oh, interesting. Okay.
Yeah. So it doesn't have to be monotone. This is just saying it's bounded, but this is a very good question. The conditions are reasonably technical, and it isn't clear what kinds of things break the theorem.
Is it just existential, or you have an algorithm?
No, I'm sorry. Yeah, so maybe I went through too quickly. So take this specific centrality measure,
and this
yes. So this works for any of these cases. So there's sort of sufficiency bounds, necessary bounds for this particular centrality. I mean, whether this is the best, etc., that's not known. And I'm sorry.
This meets the lower bound that you. This meets the lower bound that you have.
Right. I mean, it's quite general. It needs. Yeah, it's quite general. It's not always clear how tight they are. So you can try to see what kinds of results you get for specific choices.
What if your graph is sort of globally tree-like? So maybe there's sort of a few small cycles. Once you contract them, it becomes a tree. You would expect that then, and let's say these local communities are bounded in size. So you could sort of say there's some finite constant, and I can contract vertices of that many into groups such that the whole thing becomes a tree.
Very good question. Right. I mean, it would be interesting to see if something like this works there as well. I mean, and I guess there's this work of the Berkeley crowd, like Michael Mahoney, who kind of says that many real world systems look like that, like locally tree-like, globally tree-like, but locally community. Yeah.
Just to be sure, so the lower bound is also for Jordan centrality.
Yes.
This algorithm will work with budget bounded. So it doesn't not apply with other algorithms.
Very good question. Yes, no. So if one goes back to the work of Bobek, Devroy, Lugosi, for specific models of networks, they're able to analyze like the maximum likelihood estimator, and because of that, so for this model and this model, preferential attachment and uniform attachment, they basically show that any algorithm has to have the same order for those specific models.
Any algorithm should have this complex, this
right. You need at least this much. So exactly. So the question is, are there other algorithms that can do better if you're allowed to use any estimation procedure? So because of the particular structure of these two things, they're able to find these lower bounds, but trying to do this for general functions, completely open and super cool problem. Main issue being figuring out what the likelihood is, etc., is intractable in those settings. Okay, very good question. Okay, so sort of before switching to the next topic, sort of the main there's a natural question, which is, all of this requires global information about the whole network. So one question is, suppose you only have, for every vertex, you have local information, maybe it's degree and maybe a bit more information. Under what conditions can you use local information, like say maximal degree? I'm just going to go to the vertex with maximal degree, hopefully where my infection or network started is somewhere there. So under what conditions does this happen? And so I'm not going to go through this too much, but the basic punchline is there are conditions on the attachment function F for your network model, which tell you when the maximal degree works and when it doesn't. And in particular, so if you have attachment functions of the form Fk, which is k to the alpha, so degree proportional to some power, if alpha is between half and 1, then it turns out maximal degree is enough. You go to the maximal degree and your source of your network is somewhere near the maximal degree. Whereas if alpha is between 0 and less than a half, then sort of you cannot do this. So the location of the maximal degree is very far from where the infection actually started. Okay, so this is sort of the first part where somehow, because of long range dependence, there's a lot of information in the initial part of the network, which allows you to do various reconstruction problems. So the second sort of question is sort of change point detection. And so I'm just going to skip this. And so the main, so once again, the motivation is, suppose someone came up with a network model initially that for some specific reason, some evolving network model, say preferential attachment with some probability proportional to some function of the degree. Okay, so for example, this famous class of models is Barabasi-Albert model, where this function is assumed to be some linear function of the degree. And the reason they came up with it was it sort of gives a nice, simple story for why maybe real world systems have heavy tail degree exponents. So if you have this sort of attachment function, f of k equals k plus alpha, then it turns out that if you look at the degree distribution of the graph, then as n becomes large, it stabilizes to sort of a deterministic probability mass function, which has this sort of property. So the exponent of the limiting degree distribution has an exponent which is alpha plus 3. Okay, so this is sort of known, but now we can ask the following question. Suppose a network used one particular attachment function, f of k, which is k plus alpha, up to time n gamma. And then from time n gamma onwards up to n, so somewhere in the middle, there was a shock to the system. A politician came into Twitter and started using Twitter in a completely crazy manner. And so the whole Twitter, the way that Twitter sort of evolved completely changed. There's a shock to the system. So suppose this happened, then can you, if you just, let's say you're allowed to view the entire network evolution process, can you find out where this happened? What is this gamma? And so the first question we thought about was, so this is the change point model. Let's say up to time n gamma, one used one function f, and let's say that function is k plus alpha. And then after time n gamma all the way up to n, which rescaling to 1, let's say you use a different function, k plus beta. So if you use the yellow function for the entire segment, then the degree exponent, if there's no change, the degree exponent will be alpha plus 3. If you use this different function g for the entire thing, no change point, your degree exponent will be beta plus 3. So what should happen if there is a change point somewhere? Okay, in particular, just to get some idea, let's say this gamma is super duper close to 0. So the natural guess is, this stuff should determine what happens to the network. And the basic punchline is irrespective of how small gamma is, gamma could be 0.01 or 0.0000, super small, irrespective of how small gamma is, the initializer function, so the function f basically controls lots of macroscopic properties, in particular the degree exponent of the graph. So going back to this picture, it doesn't matter what gamma is. Again, gamma could be 0.00001. the degree exponent of the graph will always be alpha plus 3. The purple stuff does not change the degree exponent of the graph. It will change the degree distribution, but it cannot change the degree exponent. So I'm sort of cheating here a little bit because I'm saying the network can go up to time n gamma. So there is this n. So up to time n gamma, the network evolves according to something, n times 0.00001. And after this, the network does something else for most of this segment of n. So I'm hiding the scaling of n, but this sort of, this is what happens to the system. So, so just to sort of summarize what we've thought about, so the initial guess that, oh, you can maybe figure out what the degree exponent is, do log-log plots and try to understand changes in the degree exponent. These sorts of estimators don't work. And so one can think about more general questions. If you have some general function f that controls the dynamics up to time n gamma, and a different function g that controls the dynamics, can you actually identify this? You have no idea what gamma is. You have no idea what f and g are. Can you identify where the change point is? Yeah.
So a natural question would be, what if you actually changed the coefficient in front of k?
Right. So I guess by rescaling, I think that might just largely change. It might end up something like this. So if it's like 2k plus alpha, once you do the division, that thing comes over here. So it end up in a similar sort of class.
I see, because
preferential attachment, this divided by this. But it is a good question. I mean, what would happen if you have general f and g?
But not precisely with the change point, right?
Say that again?
When you have a change point, this argument no longer works precisely.
Sure.
You have a different f and a g, so the normalization will work a little different.
Sure. Yeah.
What would happen if gamma is changing with n? Gamma is going.
Very
down
good
to 0?
question. So I'll come to that.
Sure.
Yeah. Because I have a sexy name for it. So I would like to
I'll
use that sexy name. The only big anyway. So okay. So these are the sorts of questions. This is called non-parametric change point detection, because you don't have any information about f and g and gamma and so on. And so just to summarize in a few slides, what we managed to show with Sain, Banerjee, and Ian Carmichael is for a general under general assumptions on your f and g, you can kind of understand what happens to the degree distribution of the graph and sort of show concentration in a pretty strong sense. And using this concentration of the degree distribution of the graph, you can kind of come up with the following change point algorithm, which I'm trying to describe in words. So you keep monitoring the degree distribution of the graph. And what you do is you compare it with the degree distribution of the graph when the network is of size n over hn. And you become alarmed the first time where there seems to be a big change in the degree distribution of the graph. So this is your reference comparison, and you keep comparing this as a time series with the degree distribution at this fixed time. And so it turns out that this is consistent. These sorts of estimators are consistent. But again, there are tons of open problems, because if you actually see how these things work in simulations, it's really bad. So, difference between math and actual applications, the rate of convergence for these sorts of estimators is super bad. Okay, and so coming to Sumit's excellent question. So, one might ask, so now what if your change doesn't happen at time n gamma, but let's say square root n? So this is sort of we call it the Big Bang model. So up to time 1 to square root n, let's say, or in general n to the gamma, the network evolves according to something. But from time n to the gamma all the way to n, so time square root n all the way up to n, the network does a different evolution mechanism. So we didn't think too closely about sort of change point detection, but we thought more about structural properties. So the first thing, which seems sort of natural, should be obvious, is what happens between n to the gamma up to n. This is the thing that should sort of drive the empirical degree distribution. So if most of the time, from square root n all the way up to n, for most of the time, if you have some function f1, which is driving the dynamics, then this is what should control like empirical degree distributions. It turned out to be super hard to prove, but this at the end, this obvious result is true, that the second function controls the degree distribution of the graph. But so where does, how can you find if there is a change point in the system? It turns out for specific classes of these attachment function dynamics, change does occur in sort of these macroscopic functionals like the maximal degree. So maximal degree statistics, but this is all for specific choices of models before and after change point. For specific classes of these changes, the maximal degree does experience the change point, but not sort of bigger average functionals like the degree distribution. Okay, so now let me come to sort of last topic and then we're done. So this is sort of related to network coevolution. And so I'm going to give you two motivations, mainly because I want to advertise this remarkable result by Melstead and Chebulu in the 2000s. So, so first motivation for network coevolution is vertices. You want models where the network influences individuals, but what the individual does influences networks. The second motivation is the following. So preferential attachment type models where vertices enter the new vertices enter the systems and connect to pre-existing vertices. This somehow, most of the models assume either global knowledge of the network, all the degrees in some sense, or they assume sort of the degree is the most important factor. So both of these seem maybe not so realistic. Either, in many cases, people don't know the entire structure of the network, or in principle, even if you do believe something like this, sort of the attractiveness of individuals should depend not just on their friends, but maybe the number of friends that their friends have, etc. So let's say on LinkedIn, it's not just how many I'm attracted to someone, not just based on how many friends they have, but how many friends they have, the kinds of connections they have. So one specific such example is, for example, PageRank attachment. So suppose I'm trying to game the system, I'm trying to increase my own popularity. So what I can do is the following. So PageRank scores, this is a famous Google algorithm. So essentially, many of you know all this, but PageRank score, if for a directed graph, if you're given a damping factor C between 0 to 1, it's essentially the PageRank scores of the vertices in the network is the stationary distribution of the random walk, which has the following dynamics. So using the directions on your graph with probability C at each step, it does the usual random walk, again, using direction. So from here, I can only jump here. From here, I can jump here, etc. But with probability 1 minus C, I can jump to a randomly selected vertex in the entire network. And so these PageRank scores, they satisfy these linear systems of equations, not too important. And but the main question one can ask is, if I'm a new individual in the network, maybe I want to increase my popularity somehow. And somehow I know the PageRank scores of individuals in the network. So I connect to someone with probability proportional to their PageRank. And this PageRank score is now a more global measure of people's popularity. And so, for example, for directed trees, you can explicitly compute what the PageRank scores are, and they turn out to be, so for a particular vertex, you look at number of individuals who can directly connect to them, number of individuals who are at level 2, and so on, and you get sort of a nice exact formula, in particular telling you that PageRank scores depend not just on the degree, but in some fashion, in a weighted manner on the neighborhoods of a vertex. So punchline, so now suppose I want to change the dynamics of my model where new vertices come in and they want to connect to someone with probability proportional to their PageRank. Is this an interesting math model? Can one get anything interesting from these things, etc.? So this is the basic question. And this or maybe not weirdly, for me, it was very surprising. This PageRank type attachment model is actually similar to a completely different class of models called the web surfing model. So here maybe our motivation is, okay, all this preferential attachment, individuals come in, they somehow need to know information about the network before deciding where to connect. But the way that we find out how individuals in the network are interesting is we randomly surf in the network. We select an individual at random, a web page at random, look at where that web page points to, and then we go there, etc. So sort of we randomly explore the network, and then eventually you're like, I'm tired of all of this. Let me go and binge on Netflix. So at some point you stop. And so one can think about a co-evolutionary network model with the following super simple dynamics. Again, I'm not claiming this is very realistic, but the model is the following. So suppose you've constructed your network at time n. It's a directed graph. You start with the root, the directed graph. At time n+1, a new vertex enters the system. And so it selects a vertex uniformly at random in the network because it doesn't know where it would like, it doesn't exactly know the structure of the network. So selects a vertex uniformly at random. And then what it does is it selects an exploration, the number of exploration steps to the root variable. So how much time it's going to spend sort of walking up the tree. Okay, so again, this is very unrealistic. The random walk only uses the directions of the network. Until it gets tired, and then it goes and binges on Netflix. Okay, but once it has explored the tree, it stops there, connects to the vertex where it stopped. And so the main thing that controls all of this is this probability mass function, which controls how long this random walk sort of explores the graph. And once a vertex has done it, it's now changed the structure of the network. So just to give you an example, so let's say you start with vertex V0 and then V1 is connected to vertex V0. So now let's look at the green vertex. So C2, the choice of vertex V2 is I've decided I'm going to start exploring the graph at vertex V1. So that's V1. And then the number of steps is I immediately get bored. I look at this web page and say, that's an amazing web page, I'm done. So I connect over here. Then next, you have C3. So vertex 3, it decides I'm going to sample vertex V2. Okay, I've sampled this. And now I have 4 steps. I'm going to go for 4 steps. So in this case, I go 1 step, 2 steps, and I've reached the root. So I stop over there. Okay, so there's a condensation phenomenon where if you do end up at the root, you just stop there. There's no more. You've hit the frontiers of the internet, which of course is not exactly feasible, but that's what happens. Okay, so this is how the network evolves. Once you hit the root, you stop. But bottom line, you explore the graph for a little bit and then you stop, thus changing the structure of the network and influencing next set of random walks that come into the system. And
in the previous, there's no correspondence in the color coding, right?
No, so this is a choices. So, okay, so at step 4, this is V4 has decided to select vertex V2. So I select this, and then I'm going to go for 1 unit of step. So I've selected vertex V2, I go to vertex V1, and then I get bored and I connect over here. Yeah, so these are the choices. So C denotes the choices that I make, like where do I start exploring the network? And this represents how many steps I will go up in the network before I stop.
Let's say C4 again, goes 1 step after V2, goes to V1.
Yep.
And stops there. That's it.
And stops.
That's it.
That's
why you're done. Written a line, a pink line from, or whatever, cream line from V4 to V.
Yep.
Very nice. Thank you.
Yeah. So this is the basic model. And so the main thing I want to advertise is this amazing result of Chebolu and Melstead, I think in 2008, where what they showed is suppose your exploration model or the number of steps that you explore the graph has a geometric distribution with probability P. So what this basically means is once you have explored your graph, you decide, am I done today or do I want to explore one more web page? And the probability of this is sort of independent based on your previous steps. So if you do the geometric local exploration, then it turns out this model is exactly the same as the PageRank attachment scheme. So vertices come in and connect to other vertices with probability proportional to the current PageRank scores with this relationship between the damping factor and the probability. Okay, so these two at first are competing questions. I would like to explore the graph and then connect somewhere, or I want to connect with probability proportional to some global attachment function are actually sort of very closely related. Sort of a beautiful paper. Okay, and so what they found in their paper, and I'll tell you what we did and then I'll stop. So what they found is sort of phase transition. So if P is less than or equal to half, they found that the expected degree of the root is of order n. So there's condensation around the root. Whereas if P is greater than half, then the expected degree of the root scales like some sublinear function of n. Okay, and so this is sort of expectations, etc. But this is what they found, some sort of phase transition. And the main question is, can one develop general theory to analyze these sorts of network models? And so essentially what we showed is, as long as your expectation of your exploration step is finite, these network models converge to, in the local weak convergence sense, to limiting random trees. None of the details are too important, but maybe let me just come to the punchline. So lots of these things are controlled by how many steps you want to explore your network. And so if you look at the distribution of this, you can associate a random walk with this sort of, with this distribution. And these sorts of random walks, under some assumptions, there has been a lot of study on the quasi-stationary distribution of these random walks. So more precisely, you can ask, if I condition the random walk to do something weird, then what properties does this random walk have? So for example, suppose my expectation z is not equal to 1. That means this random walk either has a propensity to drift upwards or drift downwards. And suppose I say I start at vertex 1 and I condition that I want to come back to 0, not come back. I start at vertex 1. I would like to go to 0 eventually, but after a super long time. So if you have a downward drift, you really want to get to 0. So this is sort of unlikely. If you have an upward drift, then you're saying I would like to eventually come back, but after a very long time. Again, this is unlikely. And what Daly in 1969, what he showed is these have sort of exponential type behavior. So this scales like e to the minus n log r, where this r can be computed using information about the probability generating function of these random walks. Okay, so what is the point of all of this? It turns out very weirdly that this particular quantity, this r, controls many of the properties of this random walk. So two completely unrelated things, quasi-stationary distribution of random walks on the interval and this particular graph model are very closely connected. For example, if you look at the degrees of vertices, not the root, but vertex 1, vertex 2, and so on, they scale like this, n to the 1 over r. If you look at in the case where the expectation of z is less than or equal to 1, so you stop within time less than or equal to 1, the degree distribution of the graph converges to something, and the exponent of that is this minus r. If you, and sort of maybe sort of expected result, if expectation z is strictly greater than 1, then there's condensation around the root. So lots of these walks end up at the root. And so if you look at the degree of the root, this divided by n converges to some sort of non-trivial random variable. Okay, and so I'll just stop with this. Sort of there's no phase transition in the height. So one might think, okay, there's this condensation at the root. So maybe these networks basically look like the root with like a whole bunch of things attached to it, and then maybe just a little bit after this. And it turns out this is not true. The network itself scales logarithmically in the size of the network. It's just that in some regimes, a whole bunch of people end up at the root. Okay, so that's it. I'm going to skip all of this and stop over here. So thanks for your attention.
So while our next speaker sets up, we can have time for a few questions.
Question. So this is a slightly different direction. It's on? Okay. So if you look at a fluid as it freezes,
Okay.
It will start in some random place and start to grow a little crystal there, and that'll grow. Seed detection, I don't think is all. There are a lot of, the actual growth of that is very badly understood. So generally this is called nucleation theory, and its predictions are way orders of magnitude bad.
Okay.
So we don't actually know how that growing crystal, which we can think of as the graph, I think, we don't know how we don't know the rule as to how it's growing.
Okay.
But I wonder, in your talk, you seem to be talking more about if I knew the rule for how it grows, I could do so. So can you ever go the other way? Can you get information about that growing graph and tell what the rule was for how it's growing?
Yes, a good question. So there's work now by like a bunch of statisticians like Van der Waart, who's been looking at for network models. If you want to somehow estimate the function that determines how this network is growing, can you do it consistently? Can you derive more fine scale properties? So what we've been thinking about is more, suppose you forget all information about the vertex labels. You don't know who came first, who came. Can you find out where the network actually started from? And the main motivation is we expect these same things to work for epidemic models. So you have epidemics starting from a graph, let's say any random graph, and you get to observe some information about how the epidemic evolves on the network, like who are infected, status of people. Then can you find out who started the infection?
In particular, in your intuition here, you seem to think that there will be a starting point and that's it. But as it's growing, why isn't there it creating new seeds?
I mean, so it is. I mean, at every vertex that comes in, more people come in and potentially connect to it. Yep. But every vertex has the potential to connect new seeds or start new seeds.
Okay, we have time for one quick question, but
So all your analyses are for trees,
Right.
particularly the last one with the preferential attachment scheme with the random walker. Would you be able to do that in a directed version of the preferential attachment model where m is larger than 1?
No, so we haven't been able to do it. That's a very good question. I mean, and
You would expect similar results to hold?
it'll be hard. Yeah, I mean, no, we do expect similar results to hold. That's an
I
easy
wasn't
statement.
talking about a proof. Are you expecting the results to hold?
No, but a slightly separate question, same in the same light. There's a lot of literature now on fake popularity. Like you have new individuals coming in and making a ton of Twitter followers. Can this change the dynamics of the network? So this is related to the seed detection problem. Under which cases can this change, your ability to find who infected the graph? So yeah, very interesting questions. Most of our stuff is for trees. Okay, thanks.
okay. It seems my task to negotiate with the next speaker about the delay.